All right, today it's the middle part of the packet, problems 21 through approximately 33. Okay, and we're trying to get through a bunch of trig here. And a lot of what we're reviewing is the trig because you've just recently taken the other tests, and so they're fairly fresh in your mind. So we're going to be focusing again mostly on trig. Number 21, part A. Do you remember that on these kind of problems you graph the parent and then you just have to change the numbering and you'll have it? Do you know what the parent for cosine looks like? Everybody, please take a moment. Graph number 21A. You're just graphing the cosine. Cosine's kind of like a valley. One to -1. And then at the end, it's 2 pi. In the middle, it's pi. I shouldn't really label it there, though. Hold on. Here, it's pi. Here, it's pi over 2. And here, it's 3 pi over 2. There. Raise your hand if you had that right. Okay, good. That's a base one. You got to know these like the back of your hand. Otherwise, you're giving up on the easiest section of the test. In the past, you guys, you should think about this. The hardest section of the tests for you guys has always been algebraic manipulation. The best scores by far have been your graphing tests. That means you want those graphing problems. You want them all right on the test because those are the easy ones. Okay, and that's going to be about 1/4 of your test. And if you can lock those all in as good scores, so pay especially good attention on the graphing here. All right, so I'm not sure that it's 1/4 of the final, but it's a big chunk is graphing. So the next part here is to renumber it based on the fact that our question really isn't the parent. Our question is y equals 0.5 cosine cosine of 3x. That's important and that's important. Well, the 0.5 is just the number out front. That's the amplitude. That's this. I multiply both of these by 0.5, which is 1 times 0.5, and -1 times 0.5, and I get -0.5 and +0.5. There we go. I fixed that part. Now I'm going to go to the 3x. I'm going to remind you of an important formula. Period equals 2 pi over b. And in this problem, what's b? Say it. 3. So 2 pi over 3. So now the new period on this thing is not 2 pi, 2 pi over 3. But instead of dividing everything by 3, there's a smarter way. Times by 1/3. Very good. I'm going to times everything by 1/3. Times by 1/3. Times by 1/3. And then my new answers for these labels are pi over 6, pi over 3, 3 pi over 6, which can be reduced to pi over 2, and 2 pi over 3. This one was right, actually. So now I'm going to use my surgical eraser, a little tiny one that allows me to get in and fix things carefully. And I'm going to get rid of all this stuff where I was like showing my work. And then you can see the final answer up here. That one's written nicer, so I'll just leave it at that. There we go. Any questions about that? So, yes. I should. How about if I said it, but I should actually write it. So 1 pi over 2, also known as pi over 2. Yes, sir. Don't you graph 2 periods of this function? Oh, I didn't know. What did it say in the directions? Graph 2 periods. You're right. I didn't notice that. Okay. So that is important. That's going to happen on the test too. Seriously. And that really is a sucky way to lose a point because if you got this far, this next part will be easy to just like copy it and keep going. You know what I mean? If I've got it all labeled, now I can just keep going like that. And, oh wait, that's not far enough. I have to go all the way up to the top. I can't get there, but I have to have 2 complete cycles. And could I go to the left? Sure, I can go to the left if you want me to. I find it really hard to write like the y-axis. I am fine with doing it either way. So you can debate it for yourself which one you think is best. I'm going to just go, I'm going to use green and I'm going to go left. There we go. And it fits on my board better. So And now I'm going to say these are all, oh, that's actually kind of smart because I got all the numbers done already. And I just have to make them negative. So this is negative pi over 6. This one's middle of it's pi over 3 negative. This one's negative pi over 2. And the last one's negative 2 pi over 3. Because I can use all these over again. That was a good idea. Okay. Are there any others? Any other questions about that, or things I may have done wrong? Like I forgot to I only graphed one period of it. Watch for that, because some of the test says 2 periods of this. Some say 1 period of this. If it only wants 1 period of it and you graph 2, no point. Have to mark it wrong. Sad. Okay. Let's go to some other problems that are similar, except cosecant. Cosecant is not a parent graph. Well, there is one, but it kind of rides on the top of a different one. Let's do 21b. 21b. Remember, act like we're taking the test right now, because these questions are on the test, or ones just like them. That's why we made this packet for you, to focus it down, because we know precalc has tons of topics, and this narrows it down. So act like you're taking the test right now. In fact, one year, we actually took the review packet, and that was the test. So people turned in their review packets, and then we gave them the test, and the test had all the same questions in it. Some kids were like, they didn't even notice because they'd never done their homework. But for the kids that actually did their homework really thoroughly, the homework was the test questions. Well, would it help you? That's the question. All right, so B is y equals negative CSC, cosecant. This is probably one of the most confusing ones for people because you're not used to secant at all. When you came into this year, you never even knew what a secant was. Now you know that secant is the flip of which one? Cosine. It's 1 over whatever cosine is. And did I say that wrong? Hold on. Sine, cosine, tangent, just to clarify. Cosecant is the flip of sine. Is that one we were talking about? Where was I talking about? I must have said the wrong one. But anyway, I know which ones go together. Cosecant goes with sine, and this one is secant goes with cosine. And what's the last one? Cotangent goes with tangent. When I say goes with, it means they're not exactly equal, but they're the flip of each other. So you could say 1 over, 1 over, 1 over, and I could say now they're equal. And I should really have an angle thingy. I'm going to use theta. And there we go. Okay, so moral of the story, you need to know so much for this test, and graphing is one of those areas that should be kind of one of the easier ones for you. So let's continue with this cosecant graph. How am I going to do cosecant? It rides on the back of sine. Here's sine. Sine goes like that, and it ends at 2 pi. It has pi in the middle, pi over 2 right here, and this spot's 3 pi over 2. I would number all of it to start with. Then I would go back and redo things when necessary, like if I have to stretch it or flip it or whatever. Now I've got sine done. Is that what the graph is? No, it's cosecant. Cosecant rides on the back of sine, though, so I'm going to make it in green here. There's cosecant, and it's got asymptotes here and here. There, now I've graphed cosecant. Now I'm going to get rid of the sine graph just to make it clear that this is not part of my graph. There. Now I've graphed cosecant. But now I have to make some changes. This has a flip. So the up becomes down, and the down becomes up. There. Now I'm going to use my eraser again and get rid of these guys. There we go. There. Am I done now? No. Now there's the 3. Do you remember a formula that has to do with period? If you do, write it down on the side of your paper and I'll tell you if you got it right. Write down the little formula with period involved. If you do these, you'll remember them 4 times better than if you just watch me do it. Yes, sir. Arrows are, yes, they're an important part of the graph. Could I possibly mark it right with one of the arrows not there? I probably might not even notice. Okay, the 3 is part of this. Period equals 2 pi over b. Raise your hand if you remembered that correctly. Good. And the b is 3. So it's really 2 pi over 3. And that means 2 pi over 3. And now should I divide these all by 3? No, there's a better way. Multiply by 1/3. Oops, that's kind of sloppy. I'm going to try that again. 1/3, 1/3, 1/3. There we go. As soon as you multiply those all out and simplify them a little bit, I've got that done. Do I need to change these numbers here? No, because there was no number in the front. There's a 1 there, I guess you could say. So, all right, that's it. You start by graphing the parent. In this case, we had to graph something that rode on the back of the parent. The parent was kind of like sine, and then we graphed the cosecant, and then we flipped it, and then we changed the numbering, which effectively does a stretch or a... What is this, actually a stretch, or is that a shrink? It's a shrink because it's on the inside, so it does the opposite of what you'd expect. And that means that this thing gets over with quicker than normal. Normally it takes all the way until 2 pi to get finished. This one gets finished at 2 pi over 3. 3 times faster, you might say. Gets over with 3 times faster means it's been squished 3 times as narrow. Yes? That's considered only one period, yes. So that same thing applies, except this is so much easier to, copy and get the next couple. Just have to keep going and say, okay, it's every other one, and then it's down, up, etc. So I'll make it up, and I'll make it down, and then now I've got 2 periods. But do I have to actually number all those spots? Yes, I would. If you have areas where you have graphs, you should have numbers for all those areas. And yes, it could have been very easy for me to forget to do a second period of this function. So watch out yourself. Don't give up easy points by forgetting something little like that. All right, let's move on. Go to 22. Completely different. Here's 2 parent functions, as you should know. You know how I've been saying the log is kind of like a tree that's been blown over in the wind? Okay, well, here's the log graph. That's the parent log graph. This is the parent exponential. Do you know that they actually end up, if I do this right, they actually end up being inverses of each other? That means that they they are a flip across the line y equals x of each other. So this spot right here, for instance, is 1, 0, and that's xy being rearranged and flipped. Now, if you remember that about our inverses, but they're just a flip of the x's and the y's. This is 0, 1. It's a flip of 1, 0. That makes sense? All the points on the one get flipped, and then there'll be a point on the other one. So if there was a point right here at like 2, 8, then there must be a point here at like 8, 2. All right, anyway, this is the graph of e to the x, or 3 to the x is pretty much the same thing, right? 2.7 is what e is, so that's about 3. And then this black one is the graph of y equals ln of x, or log base something else. That's log base e. What if it was log base 10? And then I'd just say log x. It'd be a little sharper turn, but basically they'll look like that. So your log graphs look like the black one there. Your exponential graphs look like the red one there. And then from here, all we got to do is like figure out where it moved to be able to graph this thing. All right, so let's do 22, part A. 22A. So ln, that means, oh, I know that one. It's a log. Log tree blown over in the wind. There we go. There's my log graph. Except with this one has to move where? Left 1. So if this is the asymptote right there, now if I want this thing to move, I'm going to grab it and move it left 1. I'll grab the asymptote, move it left 1. Oh, great. It made little tiny pieces of asymptote. There we go. There. It says make sure to include asymptotes. I did. All right. Look at D as in dog. Seems too easy. I'm doing 22A. Is that okay? Maybe I moved over 1, but did I move over like a little too far for you? Does it? Okay, hold on. 22, oh, I already wrote that. 22a, make sure we're all doing the same one here. It says ln of x plus 1. That's the one I'm doing. Is that what the one you're doing? Okay, just hold on. Does this mean left 1? Okay. Would you agree that the original starts like there and there? Maybe you can argue with how far over I moved it, but I was trying to move it to the left 1. Okay. I guess I moved it too far for you. I'll try moving it not as far. Call this one over. So, now how close, do you get that it's going to get closer and closer to -1? Do you know the asymptote moved? It used to be at 0. It would never have touched 0 before. Now it's got to move over 1. So now it can be over here, and it's never going to touch -1. Get the difference? Do you agree that the parent one never touches 0? So have I got it about right for the parent one now? Something like that? Should I move it down a little bit more? Is that better? Okay, but the point is that it never touches 0 originally. Do you get that? Here, I'll even do it with really sharp, crisp lines. That is the asymptote line. And it's supposed to get infinitely close to that, which means it pretty much touches 0. It doesn't touch it, but pretty much touches 0. So then when I move it over 1, shouldn't it pretty much touch -1? Okay, so then it's only just splitting hairs about how far over I moved it. I mean, come on. Okay. Let's move on to a different one. Let's do 22D as in dog. And that one is log base 2. Since it has a base 2, it's not going to be quite as sharp a turn. 4 minus x. I'm not going to put 4 minus x because I'm a rebel. I'm going to say -x plus 4. Why? Because that helps me see that there's a flip in there. That's not just a subtraction. That was a flip over the x-axis. No, wait. It's a flip on the inside, which is a left-right flip, which is over the y-axis. Okay, so if I'm going to get the parent log graph, and again, logs, trees blown over in the wind, so like that. Okay. You guys have been so picky with me. I'm going to do this carefully. So there. We okay so far? Now where should I move it? Should it get flipped first or should it get moved first? I heard some people say flip. I heard some people say move. Okay, the math way to decide this is what's normally first. Multiply by -1 or add 4. What's normally first? Multiply. So we should add. So we should do the plus 4, which is move it. And which way? Left 4. Here's left. And we can argue about how far 4 is, but something like that. Left 4. Okay? Now, how about that negative in front? Does that a flip? Which way flip? Left, right. Now here's a big mistake people make. They go, oh, I'm going to go across the asymptote line. You don't flip it that way. It's not flipping across the asymptote line. It's flipping across the what? It's a reflection over the what axis? The y-axis. So if it's going to go over this asymptote line needs to move over there now to go across that axis. And this needs to reflect. So I'm going to draw it, and I know some people are good at seeing these kind of things, and other people are terrible at seeing these kinds of things. But I'm going to move it over here, and it's the green one now. See how the red one and the green one are a flip of each other? And you got the asymptote had to go across that y-axis. It used to be over here. Now it got reflected over there. All right. What? So the green one's the answer, yes. The red one was just moved to the left. Now the green one's a flip. So now that's gone. Yes? It's all right. That is correct. Yep. All right, now, what if you had to prove it? What if I had to prove I was right? What if you guys were saying, no, 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 you were totally wrong. I could prove it. I could prove it with the XY chart. And that's probably what you should do to check yourself to make sure you didn't screw it up. X and Y. What are some things that would be nice to have in here underneath this scribble? What would be nice if it was in there?
-2.
No, because you can't allow, you're not allowed to have a negative right there. Try again. A 1, because if you've won the argument, you get 0. So if I want this to become 1 in there, what do I got to put in for X to make it actually work? To make it equal 1, how about if I put in X is 3? Does that make sense? I'm going to put a 3 right there. Just put it, please. So this is -3 plus 4 makes 1. So I just made this inside 1, so it's log base 2 of 1, and if you've won the argument, you get 0. 3 comma 0 should be on my graph. Does it look possible that 3 comma 0 could be on my graph? That's that spot. Okay? Now let's try another spot. Anything else you want to stick in there? 2. I'm hearing that we should make this whole thing equal 2. How can we make that whole thing equal 2? If X is what? If X is 2, it actually works, because I put a 2 there. It's -2 plus 4, which makes 2. Log base 2 of 2 is 2 comma 1 should be on my graph. Over 2 up 1. Hey, looks kind of like it's on my graph. So I got 2 points that worked. I must have done it right. You know what I'm saying? Now that is a dangerous place, because if you screw up your XY chart, you might think you put it in the wrong spot, even if you didn't. So I would trust where you thought it was supposed to be to some extent. So if your points aren't working out, maybe you're goofing them up. Yes. Yes, I want you to have an XY chart, and I want you to have at least 2 points. But if the directions don't say that, you won't be bound by that. Do I want you to? Yes. But you are only bound by the directions on the test. And the directions, I guarantee you, are going to say something about the asymptote has to be in the right spot. So make sure that's not in the wrong spot. Not necessarily. It would be good. More labeling is better, but I'm not making that a rule. Okay, well, let's move on. Look at 23. The amplitude 2. Oh, this is a really common screw-up. People go, okay, so you're telling me that this distance, the amplitude, is 2. No, that's not how we do amplitude. If the amplitude's 2, how much would the whole distance be right there? 4. Do you get that difference? So then, when they say that the lowest spot was what? What does it say on 23A? The lowest spot, the minimum, is -6. Okay, I better move this thing down. There. Something like that. So the lowest spot here is at -6. I'm going to extend my axis down here and say this is -6. Okay, see how my low spot's at -6? Then the amplitude's 2. People go, oh, so this is 2? No, that would be 4 then. And what's the highest spot then, the maximum? -2, because it was at -6. Now it goes up 4, and now it's still at -2. Make sense? You should try the other one that's like that. All right. Go on to number 24. 24A. All right. It's got a graph, and that graph to me looks like sine. But it's been stretched a little bit and squished a little bit in a different way. Do you get that it goes up to 2 where it normally would only go up to 1? And then look at the period where it finishes a complete cycle. You know, if it starts here at the origin, it finishes its complete cycle when it hits right there, and it's done one up part and one down part. There, that spot on your graph is pi. But wait a minute, that's not normal. So what you want to do is compare this to normal. So here's normal. Normal would be y equals sine. But this isn't normal. So how should I change it? 2 sine. Yep, that's the amplitude. Got that fixed. Now how about that pi? Do you get that that's messing with the b term? That's what makes these numbers different, is the B term. That should go right there. Want any guesses? We can just try it and see if it works. 2? Let's try a 2 there. So period is supposed to be 2 pi divided by whatever's there. So if I put a 2 there, is this going to work? Yeah, because 2 pi over 2 is going to cancel out the 2's. It'll be pi. The period will be pi, and that's what we want. See? It's pi. So yay, it worked. And so that means this is our equation for that graph. Part B, can you tell that that's cosecant or secant? If I were you, I'd sketch in what sine would look like and say to yourself, is this writing on the back of sine? No, it's not. And then maybe for B, you should sketch in cosine. And you go, oh, it's writing on the back of cosine. And then you just got to try to figure out how much it's been stretched and stuff. So what's that function that rides in the back of cosine? Secant. So part B is y equals something secant of something. So B is a secant graph. Okay, number 25. Turn to page, well, whatever page that is. It has number 25 on it. ln x minus 6, and they want the domain and range. Well, first I want a picture. If I'm ever asked domain and range, I want a picture. Here's ln x, and then how do I do the minus 6? Where do I move this thing? Down 6. Now I'm going to put in the asymptote. I'll do it carefully here. Okay, there. Do you get that I graphed it and I moved it down? Now, what's the domain? Domain goes this way. How far will this thing go from left to right? From 0 to infinity. Good. That's your domain. How about your range? That's up, down. How low to how high? It'll go to negative infinity. It'll go forever down. Positive infinity. Yes, another way to say that is all real numbers. All right, so once you have a picture of your function, it's not that hard to do its domain. That's left, right, and its range, which is up, down. I will warn you that secant is like, and cosecant are virtually impossible to do their domain because they have all these asymptotes running through them. So I'm okay with you not doing the domain on E and F. If you try them, you'll just get really confused. You can do the range, though, because the range isn't that bad. On secant and cosecant, well, here's what secant and cosecant look like, basically. You know what I'm talking about? So if I'm going to do the range, it's like everything works except between -1 and 1. Know what I mean? You can ask me instead of them. You were asking about. Okay. Let me finish up the secant thing, and then I'll go back to that. So if this is riding on the back of sine, this is cosecant, actually. So this is the graph of cosecant. And how would I do its range? Its domain's a pain in the butt because it's got all these asymptotes that stop it. So I'm saying you don't need to do the domain. But you can do the range on this. The range on this would be from negative infinity until it hits -1, and then it stops working. Actually, it does touch -1. Union with, it starts working again at 1, and it goes to infinity. That would be an example of doing the range for the secant graph. Okay, now question. Or that was cosecant, actually. That was F. Back to 25A. Yep. I know that black line looks like it's leveling off and that there's an asymptote here, but is there actually an asymptote there? Have you ever had graphs where there's an asymptote that's crossing another asymptote like that? No, there's no asymptote. So it's rising, it's just rising slowly. This is going to keep rising forever. See what I mean? I know, that's kind of deceiving, but you have to understand there's no asymptote stopping it, so it's going to keep rising. Yes? What about the graph of cosecant? Okay, hold on. Okay, I'm back to cosecant now. So now, I already mentioned that this was riding on the back of sine, and so this would be cosecant. Okay, so I got cosecant here. Now, what's your question about it? I get what you're saying, but do you think there's an asymptote like right here? No, there's no asymptote. Asymptotes are different than spots that are like the low spot in a graph. It's not like every spot that has a low spot in a graph has an asymptote. On the other hand, if you're getting closer and closer to something, like for instance the log graph, and it gets closer and closer and closer but never touches zero, there's an asymptote like that. It's those kind that have an asymptote. It's not kind like this that have a low spot. That does not have an asymptote. Okay, so let's look at, we're getting closer and closer here. Number 26. You got to understand those graphs. That's a special kind called the basic logistic graph, and it looks like this. And it gets closer and closer to some upper limit, and it always has an asymptote at 0 also. You remember those? That's number 26. And now the only other thing I haven't told you is, you know, the top number of the function is the highest it can be. So in this case, it's 12 is the top number in the function you see there. And then the bottom number is 0. And what are these? These are y equals 12 and y equals 0, and those are horizontal asymptotes, otherwise known as horizontal asymptotes. And then they ask for the y-intercept of it. Finish this sentence. The y-intercept is where what? X equals 0. Good. I'm glad this stuck in some of your heads. So if I take this function, y equals, or f of x equals, 12 over 1 plus 2 times 0.8 to the x, then if the y-intercept is where x equals 0, I'll put a 0 right here, and then 0.8 to the 0 becomes a 1. 1 times the 2 makes 2. Add the 1, and it makes 3. 12 divided by 3, the answer is y equals 4. So to find your x, your y-intercept, you set x equal to 0. And it works the other way too. The x-intercept is where what? Y equals 0. Okay.
So after you find the y-intercept,
It asks you to find the y-intercept, so you write that down once you found it.
then you adjust your graph.
It doesn't ask you to graph it. And the other one said the horizontal asymptotes are what and what, and I showed you where those horizontal asymptotes were. But as far as adjusting the graph, we just now know what that spot is right there. We know that spot is 4. Okay, anyway, they didn't ask you to graph it though. I don't know what you just said.
Like, if you're just writing down the answers, you say like y equals 4 instead of just y equals 2.
I'm sure y int equals 4 is probably better than y equals 4, yes. If you really want a neato answer, the y-intercept is where x equals 0, so you should say 0, 4. That's a great way to say the y-intercept. All right, I would have accepted y equals 0, but it would be better to say 0, 4. Okay, let's move on to 27. Find the values of all 6 trigonometric functions of the angle theta. Okay, so it goes like this. It's got this is 7, this is 11, this is theta. Renewed burst of energy here. We just have about 5 more minutes. Can you handle 5 more minutes? Stay with me for 5 more minutes and you'll be done. Okay, so if this is 7 and this is 11, do you think I might need this side right there? Yeah, that's going to happen a lot. You need triangles that have all 3 sides labeled to be able to do all these functions, because you'll need the hypotenuse eventually, right? So this is the square root of 11 squared plus 7 squared, 121 plus 49, so that makes 170. So square root of 170 is what we use for that from now on. And remember that way of doing it. You do the square root and you either square these and add them, or square these two and subtract them. Depends on the kind of triangle it is. All right, so now if I want sine of this, it's opposite over hypotenuse. What's opposite from here? The 7 is over the hypotenuse. If I wanted tangent, tangent would be opposite over adjacent, 7 over 11, etc. You want all 6 functions for that one. Moving on to number 28. Again, drawing triangles becomes your paramount task here. You got to try to figure out where to draw that triangle. So the cosine is 5/11. Cosine is therefore positive, which rules out a couple places. All students take calc. If cosine is positive, it's either here or here, and it can't be here and it can't be here. Okay, and if cosine is positive 5/11, I'm just going to, since I don't have any more information, I'm just going to take the easiest case, which is right there. And cosine is adjacent hypotenuse. And that means I better forget that other number. Square root of, remember this before? Is it 11 squared plus 5 squared, or is 11 squared minus 5 squared? Minus. So 11 squared is 121 minus 25, and that's going to be 96, I think? Square root of 96? Yes, it is. Okay. So now, what's the sine, cosine, tangent of all those angles of theta? Or sorry, all those functions of theta. Sine of it is opposite of hypotenuse. Here's opposite, here's the hypotenuse, root 96 over 11, etc. All right, moving on to problem 29. Problem 29, cosine of 9 pi over 4. That's not hard. It seems like it at first, but you just got to figure out where 1 pi over 4 is first. 1 pi over 4 is right there. So where's 9 pi over 4? You just kind of count it up. That's 1 pi over 4. That's 2 pi over 4. 3 pi over 4. Count it with me. What's that? 4, 5, 6. Come on, keep counting. 7, 8, 9. There we go. It's right there. That's 9 pi over 4. Is there other ways you could have got there? Sure, but that's the way they wanted to do it. 9 pi over 4. Now that spot right there creates a triangle, and it happens to have a 45-degree angle in it because that's the same as pi over 4, and that means it's a 1, 1 root 2, and from there it's not too hard to figure out the cosine of that. Cosine is ca adjacent over hypotenuse. Again, once you've got your drawn triangle, these things become easy. Now let's go to number 30. Oh, question? Oh, it's just a hand. Okay, number 30. Number 30, it tells me a point. By telling me a point, they've told me two sides. That's the thing I want you to remember for that. 3 comma negative 5. Didn't they just tell me two of my sides of this triangle? By telling me 3 comma negative 5, they told me the x is 3, that's this way. The y, up-down distance, is negative 5, that's this way. And can I figure out that third side? Sure I can. A squared plus b squared equals c squared. And it would be square root of 25 plus 9. Thank you. Square root of 34. From there, what do they want? They want all 6 trigonometric functions. Oh, can you have a negative hypotenuse? No. All right. So this angle, final answer, I want all 6 functions of this. And what have I said before? If you've got the triangle, it's easy. Sine of this, cosine of this, tangent of this, and then you just flip them all. No big deal. All right. Let's flip now to problem 30. Let's do 31 quick. I hate to, but I need to. So 31. Cosine theta equals 2/3. Where are you? Probably positive. Well, that gives me 2 choices. Where's cosine positive? Those 2 spots, right? So can't be here, can't be here. Okay. Does it have any more information that tells me where I should go? Oh, yeah, it says cotangent is positive. What does that mean? That's the same as tangent, because cotangent and tangent are like sisters of each other, right? So tangent's positive. So where's that? Which of these 2 has tangent being positive? Only in the A area, yep. So that one's out, so we must be here. And then, once you've got the triangle drawn, you're almost done, right? Cosine, ca, adjacent to hypotenuse 3. This one's square root of 9 minus 4, which would be 5, square root of 5. Okay. And then you'll just have to figure out what sine and tangent are. Once you've got the triangle drawn, that part will be easy. Okay. Last thing I want to do with you is problem 33A. Inverse sine of root 3 over 2. Do you remember that we rewrote these things? So instead of inverse sine, we could say sine of what? Theta is equal to root 3 over 2. Excellent. Does that mean I'm looking for an angle or I'm looking for sides? Looking for an angle. See, you can tell that now. All right, if I'm looking for an angle that this will work for, Where is inverse sine allowed? Do you remember this one? From here to here. If you haven't got that in your notes, that's where inverse sine and also inverse tangent are allowed. And the other one here, what's that one for? Inverse cosine. Good. Okay, so back to this. If I'm only allowed to between here and here, and I know sine's positive, see, because there's no negative sign, then I must be in there, and I can't be anywhere else. There, I got it narrowed down. It must be a triangle right in there. And now I can label my sides, figure out what the other side is. From there, it should be easy for you. I'm just trying to figure out what angle that is. So it's in a 30, 60, 90, so hopefully you can finish the deal and get that. All right. So that's my video for today that's covering up through problems up to 33. One more thought. When you're doing problems like 33G or H, where do you start? Start on the inside, and I'll warn you, some of those are really tricky. They're going to make you wish that the school year was over, but 72 hours from now, it will be math-wise. I think for you guys in math, I think you have 3 days. So anyway, okay, that's all I got for you.